Welcome students to the video module on Fraunhoffer diffraction due to N slits. In the previous module we explained Fraunhoffer diffraction due to single slit. Then we learned Fraunhoffer diffraction due to two slits. Now many number of slits of slit width A and separation between slits D. You can see in this figure that there are n number of slits illuminated by a light of wavelength lambda. The slit width is A and the separation between each slit is D. A screen is kept at some distance from the slit positions and a lens is used to concentrate light onto the screen. Here also diffraction pattern forms on the screen. The pattern formed will be in this form. You can see that there will be principal maxima, many principal maxima and minima. Like you can see n equal to 0 or 0 order principal maxima. On either side of this 0 order principal maxima there will be first order principal maxima. Then there will be second order principal maxima, then third order principal maxima. And in between two first orders, that is plus first order, minus first order on both sides of the 0 order. So this is minus first order, this is the plus first order. In between that there will be many principal minimas. You can see here secondary maximum and minimum there. Okay, so this type of a diffraction pattern forms. So the diffraction pattern consists of principal maximas, minimas and secondary maximas. All these are principal maximas. These are principal maximas, 0 order, first order, second order, like that. And at the bottom you can see secondary maximas and minimas there. Now we have to find what is the reason or how this forms. The diffraction pattern on the screen can be considered as the diffraction formed due to different positions of a single slit. We know that there is a single slit here. Many single slits are there. So if there is a single slit itself, that forms a diffraction pattern due to the formation of secondary wavelets from many points on that slit. At the same time, there are a large number of slits. Each slit contributes to the diffraction pattern. So actually the diffraction pattern on the screen comprises of diffraction formed due to many points, secondary wavelets from many points on a single slit, and such n number of slits are there. They all contribute to the diffraction pattern. Now you can see the expression for intensity due to single slit. The intensity due to single slit is, I have just marked as I1. Okay, it is equal to square of amplitude. Every time it is square of amplitude, it is a square sine square alpha by alpha. The amplitude is a sine alpha by alpha. We explained this in the case of the single slit diffraction experiments. You may refer that video for more explanation on this expression. So the intensity due to single slit is I1 equal to a square sine square alpha by alpha square, alpha square. What is this alpha? 2 alpha is the phase difference between any 2 points, wavelets emanating from any 2 points on a single slit. 2 alpha is the phase difference between the waves emanating from any 2 points on a single slit. And how? And we know if the path reference is a sin theta. Between any 2 points, this also we derive. So, the path reference is a sin theta. Then the phase difference 2 alpha is termed as a phase difference here. Okay, 2 alpha equal to 2 pi by lambda times a sin theta. Lambda path reference equal to 2 pi phase difference. That is why if you have the expression for path reference, you can find the expression for phase difference. So, 2 alpha equal to 2 pi by lambda times a sin theta. Okay, that is the contribution from a single slit. And similarly, there is a contribution from n slits. You can see here, this is the contribution to the intensity from n slits. Sin n beta by sin beta, its amplitude square. So, if there are n slits, n slits can be considered as n points. Okay, so these n points forms a diffraction pattern there. So, what is the expression for the intensity? Intensity I equal to some maximum value E times or we say amplitude. Amplitude is equal to a maximum amplitude E0 times sin n beta divided by sin beta. Okay. So, here beta value cannot be neglected in this case. So, square, we take the square of that, you will get E0 square sin square n beta by sin square beta. What is this E0? That is amplitude that is due to single slit. So, that is why you can see both the expressions here in this. Okay. So, the total intensity due to n slit can be I equal to square of amplitude, that is a square sin alpha by alpha whole square times sin n beta by sin beta whole square. Intensity due to a single slit is taken as the amplitude actually. This the circular term is the amplitude here in this case. Now, when this takes a maximum value, so this is expression I equal to I0 sin square alpha by alpha square sin square n beta by sin square beta. The principal maxima occur when sin beta equal to 0. The principal maxima occurs when sin beta equal to 0. We are not going to the mathematical derivation of this, but only keep in mind that for maxima or minima, the first, it is actually a pure mathematical step. Okay, maxima minima occur when the first derivative of the function equal to 0. So, from that we derived this condition. Okay. So, it takes the maximum value when sin beta equal to 0. So, what is the condition for sin? What is beta? Beta is, okay, that also we have to derive. Beta, 2 beta is the phase difference between waves emanating from 2 slits. Previously we learned 2 alpha. 2 alpha is the phase difference between waves emanating from different points of same slit. But 2 beta is the phase difference between waves emanating from 2 separate slits. That is the difference. Okay. So, 2 beta equal to 2 pi by lambda times path reference. What is the path reference? It is a plus d sin theta. This is slit. So, slit of width A and the slit separation is d. So, the separation between 2 such slits is a plus d. Understood? That is why here we took path reference equal to a plus d sin theta. So, phase difference equal to 2 pi by lambda times a plus d sin theta. Okay. Now, to the common expression. So, where the principal maxima occurs. Principal maxima occur when sin beta equal to 0. So, what is the condition for that? Beta equal to, beta must be equal to a multiple of 180 plus or minus n pi, where n equal to 0, 1, 2, etc. So, substitute the value of beta. What is the value of beta? 2 beta is 2 pi by lambda a plus d sin theta. So, beta is pi by lambda a plus d sin theta. There was a 2 here. 2 beta is 2 pi by lambda a plus d sin theta. So, we cancel that. Okay, that must be equal to plus or minus n pi. So pi cancel from both sides, remains a plus d sin theta equal to plus or minus n pi. So when n equal to 0, that corresponds to the 0 order principal maxima. You can see in the picture that is this corresponds to n equal to 0, the 0 order principal maxima. And similarly, when n equal to 1, 2, 3, etc., in this equation, that positions corresponds to the first order, second order, third order, etc., principal maximas. Okay, so that is the explanation for the formation of first 0 order, first order, second order, third order principal maxima in the case of n-slit diffraction. Now, for minima to occur, sin n beta in the expression for intensity, minima occur when sin n beta equal to 0, the numerator, sin n beta equal to 0. That is possible when n beta is a multiple of 180 degree, plus or minus m pi sin 180, that is it. N beta must be equal to plus or minus m pi. But what is n beta? Substitute for beta. Beta is pi by lambda a plus d sin theta. That must be equal to m pi. And simplifying, you will get n times a plus d sin theta equal to plus or minus m lambda, where m is 1, 2, 3, etc. n minus 1, n plus 1. There is no n. N is omitted. Similarly, 2n is omitted. And similarly, 0 is omitted. Similarly, 3n is omitted. These positions are not there because those positions corresponds to the 0 or the different order principal maximas. That is why 0 is not there, n is not there, 2n is not there. Okay. So minima occur when m equal to 1, 2, 3, etc., n minus 1, n plus 1, etc. So that is why you can see between two principal maxima there are minimums. Here all minimums are there. The number of minimums are there. How many are there? N minus 1. From 1 to n minus 1. So this is 0 maximum. And this is n maximum, and that's one maximum there. So in between this there is 1, 2, 3, etc., n minus 1 minimums are there. This here, n that much minimums are there. If there are that much minimums, then there will be secondary maximums also. That also is shown there as secondary maximum. So principal maximum, in between that a number of minima and number of secondary maxima. Such a wave pattern forms due to n-slit diffraction pattern. Okay. So I hope this formation of n-slit diffraction experiment or pattern formation is clear. Okay. Okay, students, thank you.